right, raise your hand if you can tell me how many electrons does carbon have? 4. So we got carbon. How many does hydrogen have? 1. So we got 4 hydrogens. Okay, this is one way of showing your CH4. You again could do it this way as well. This is called a structural formula. And this one here is the Lewis dot structure. If you look at NH3, NH3 looks like this. And H2O. Now, if you look at these Lewis dot structures, do they show the shapes you made?
No.
No, these do not show the shapes. Okay, what you notice with the methane shape, okay, when you try to separate out the electron domains by the greatest angle, some of you did this originally, you did a cross. Okay, a lot of people do a cross first, and they say it's far apart, they're all 90, it's the furthest they can be. However, you're only considering 2 dimensions. You got to consider the 3rd dimension. So some people stick one on the top and say, look, that's 90. That's 120. But are they all as far apart as possible? No, they're not. You have to then extend it to this shape right here, where the angle is about 109.5 degrees on all of them. Now, the interesting thing about an electron domain is it's the space occupied by these 2 electrons. It could be a bonded pair or a lone pair. These hydrogens, as they were represented, okay, the electron domains prefer to be as far apart as possible from one another. This is the rule. It's basically the one and only rule you need to follow. If we take these 4 balloons and pretend that they're electron domains, these 4 balloons are right now in a crisscross arrangement. But they are not as far apart as possible from one another. They want to be in this shape right here, which is called a tetrahedral shape. It is the most stable shape for all molecules. The most stable, it's a 3-dimensional shape called a tetrahedral. And this one's a little bit weak, but that's okay. This tetrahedral shape is when all the electron domains are as far apart from one another as possible. This basic shape controls how most small molecules are shaped, and when you take one of them off, you get the shape of ammonia. When you take another hydrogen off, you get the shape of water. So all we did was we took a hydrogen off, and we made these new molecules. However, the angle between the electron domains does not change very much. Okay? The basic shape is always the tetrahedral. Okay? Now, electron domains are also called electron pairs. Bonded pairs, single, double, or triple, and lone pairs are all electron domains. Electron pairs can include all of those things. Okay? Now, these electron pairs are involved oftentimes in covalent bonding. Here we have carbon bonded to carbon. You'll notice that there is 1 electron domain here between the 2 of these. That's called a single bond. It's also called a sigma bond. Sigma and single sound similar, but they don't mean the same exact thing. Now, this is called an electron domain. If you have a double bond, this is still called an electron domain. If you have a triple bond, this is still called an electron domain. It's not 3 electron domains, it's just 1. It's just 1. However, they come up with a new name for the ones that are not the first bond. First bond is a sigma bond. So all of those ones in greens are sigma bonds. Those are the initial bond or single bond, as you would think of. And then when you get into the second bond there, the second bond and the third bond are all called pi bonds. Okay? So sigma and pi bonds, okay, will help us understand some of the types of covalent bonds we can have. Now, a sigma bond is defined as the first bond to form between any 2 atoms. It forms between atoms. in our little gumdrop activity, we only dealt with sigma bonds. There were no pi bonds at all sigmas. Okay? A pi bond is the second or third bond to form between two atoms. This forms above and below the plane of the molecule. So this bond actually occurs above and below at the same time the plane of where the molecule might be found at. And what happens is when you start to have double bonds forming, the molecule, instead of being completely three-dimensional, it can flatten out a little bit. If you have a double bond with two single bonds, it creates a flat structure. And we'll look at that structure in just a minute, what it looks like. It's a different type of structure than the ones you just made. Now, VSEPR. VSEPR is a abbreviation that stands for valence shell electron pair repulsion theory. Now, the good thing about it is you do not have to know what it stands for at all. It is electron domains prefer to be as far apart as possible. That's it. Valence shell, well, those are the electron domains. The electrons are on the outside shell. Electron pair, those are electron domains. Repulsion, they tend to repel each other. So that's what VSEPR means. Now, the Lewis structures, as you could tell us how the atoms are connected, but not their shape. So it never tells us the shape unless we're really lucky, and we just draw it that way. The shape of a molecule can greatly affect its properties. Okay? Molecules and their different shapes. You remember the vials we smelled earlier this year? One smelled good, the other smelled different? All right, now, those are what are called isomers of one another. The thing that makes them smell different is the fact that they have different shapes. Their shapes are different. They have different arrangement of the atoms, even though they have the same atoms. Because of that, it affects the shape. Okay? VSEPR allows us to predict the geometry. So, predicting the shapes of molecules. To predict the shapes of molecules, look at the sigma bonds and the lone electron pairs surrounding the central atom. So we look at the individual single bonds, or sigma bonds, and the lone pairs. The pi bonds do not matter in predicting the shape of a molecule. The electron pairs, which are also called electron domains, move as far from each other as possible in how many dimensions? 3 dimensions. So don't forget you got 3 dimensions to work with. Okay, oftentimes people will be like, oh, wait a minute, it goes one's here, one's there, that's far apart. But they're forgetting about the fact you got 3 dimensions to work with. And that we saw that with our tetrahedral shape. Lone pair electrons actually require more space than bonding pair electrons. Slightly more space than a bonded pair. Okay? And so it changes the angle just a little bit from that 109.5 degrees. Now, that 109.5 degrees is called a tetrahedral shape. Let's see if I've got a tetrahedral shape made. Okay, here's a very small tetrahedral shape. A space-filling tetrahedral. If we take this tetrahedral and we drop it on the table, and we drop it again, and we drop it again, it always looks exactly the what? Same. It is a symmetrical molecule. This one happens to have 4 identical things on the outside and 1 thing on the inside. We could say it's whatever we want. We could say it's methane if we wanted to. That red thing represents a carbon, let's say. Okay, again, you can create your model to represent what is really happening. It's just a model to show the 3 dimensions. Now, the angle between each of those hydrogens in that model is 109.5 degrees. Okay, in 3 dimensions again, it's not 90, 109.5. Now, electron pairs. Lone pair electrons repel other lone pair electrons. So they repel one another. They want to, again, be as far apart as possible. Bonded pair electrons repel other bonded pair. They want to be as far apart as possible. These do not quite have the strength that these do. Okay, so it's a slight difference, a very small difference. It sometimes changes the angle a small amount. Lone pair electrons repel bonded pairs electrons. And lone pair versus lone pair is greater than bonded pair versus bonded pair repulsion. Does that make sense? Lone pairs, greater repulsion in general, so when they're repelling each other, there's more repulsion. Repulsions will maximize the angles between bonds. So it changes the angle between the bond because of that repulsion of those electron pairs. Now, VSEPR, the number of electron pairs determines the bond angles, the underlying structure. The number of atoms determines the actual shape. So, the number of electrons helps us determine bond angles and the underlying structure. This underlying structure for most molecules is a tetrahedron. Most molecules, the most underlying structure is a tetrahedron. Not true for all, but for most of them. Now, the number of atoms determines the actual shape. So if you have an atom there or a lone pair. In ammonia, you had 3 atoms and a lone pair. So that shape was similar, but not exactly the same as this tetrahedral shape. When you take one of them off, whoop, if this was NH3 ammonia, does it look exactly the same? No. It has a lone pair here, but that lone pair is not an atom, and so it does not have the same exact shape. It has the same underlying structure, tetrahedral, but its shape is called something different when that is taken off. So what are the basic shapes that we made? The first one here, CH4, NH3, H2O, HF, and Ne. We made 3 of these. If you look at all of them, they all look like what shape? Tetrahedral. Only difference is these things here represent lone pairs. So Ne has how many lone pairs around it? 4 lone pairs. Ne would look just like a single dot, a single point. It has no particular shape, a single point. This one here has 2 things connected together. So instead of calling it a point, you call it a bond. 2 points make a what? Line. That's a line. And then this one here, well, that's not a line anymore. It's not a straight line, that is. And so this one here has a different name. It's called bent, because it's not a straight line. It's bent. Some people, they get really technical, like it's called angular, because it has an angle. But that's your choice. Some people also call it Mickey Mouse. But Mickey Mouse doesn't quite do it, because the AP Chem people don't usually grade on Mickey Mouse structures. But there's Mickey Mouse. Oops. Mickey Mouse. There you go. You have the 2 mirrors. Right. It's better if it's black. Minnie Mouse, whatever you want. All right. Yeah, if it's a black carbon in the middle, it looks more like Mickey Mouse. So we've got tetrahedral as the basic shape. Ammonia's basic shape is called pyramidal. Water's basic shape was bent. HF was linear, and Ne was point. So these basic shapes here are some of the basic names you want to be familiar with. This time we're going to look at how these shapes are made, specifically using VSEPR theory. So one way of doing this is what is called using the steric number. Now, steric number, this is one way of approaching how to figure out the shape of a molecule. The steric number is the number of lone pairs plus the number of sigma bonded electron pairs. Okay, so it's got an easy acronym, AX. The A stands for the central atom. The X stands for the bonding atom. And the E stands for the lone pair. What's up?
Why is it an X?
Why is it an X? Well, X isn't found on the periodic table, so they use X for something outside. The central one, some people used to do this as C. But C is carbon. People get confused. So they use the letter A to represent the middle one, and X represents the outside. E is easy, representing lone electron pairs. The acronym is easy. I'm not saying what's inside of it is easy. CBL. Huh? Now, the good thing about steric numbers is I did not invent them. And the second good thing about it is if you have visualization skills, you may not even need to use them. Some people can do all chemistry without using steric numbers. But this is a technique that some people really like, and I'm going to teach it to you because it is very easy to use. So, let's see how it works. Let's look at this molecule here, okay? A little more advanced than our tetrahedral structure, that's okay. We've got Xe. So, Xe, we've got 4 things around it, right? And we have how many lone pairs around the central atom?
A lot.
Nope, 1, 2 pairs. So that's there, 2, 4, 8. Okay? So AX4E2. The steric number for this is going to be 4 plus 2. Steric number is 6. Now, just so you know, steric number is, you look at the central atom. How many bonds are around the central atom? 4. How many lone pairs? 2. I call bonds and lone pairs electron domains. So how many electron domains? 6. That's called steric number.
What is this called?
I'm just saying, why don't they call it electron domains? Is that there's a lot of debate. Some people don't like electron domains. So,
What's the point of the A?
I didn't make this up. The point of the A is to represent that there is a central atom. Hey, I'm not saying anything about steric numbers. There is an advantage to them at times. Yes? You could. But usually what I do is I look at each central atom individually to get the shape of each one, and then you could have the shape of each underlying one. But I do see how that would come in handy. Yeah? 4 electron pairs. It'd be 4 and 4 for the total number of 8.
Except that's not really likely.
It sounds almost impossible.
That's like 16 electrons.
It would be very unlikely, but we would have to look at that for xenon. Xenon's the only one that's been known to do some weird things. All right. Now, people are asking, okay, why is the steric number important? Once you have the steric number, the good thing is you have all of the different 3-dimensional shapes. Now, based on the models we just made, the reason we made those models is because I think it's easier to get a visual once you have the models. The first one, diatomic. You got 2 things. It's going to be linear or diatomic. Some people don't call this linear because it's 2 points makes a line. Duh. Of course it's going to be in a line. There's nothing else it can be. But here, when you have 3, it will not always be linear. Right? With water, it's not. So, you have to have a steric number of 2 in order for it to be a 180-degree angle in a straight line. Here, this is the one a lot of you made for ammonia that I said was wrong. It doesn't work for ammonia because this one has to have only 3 bonds around it, and it's missing a lone pair. It has no pairs of electrons here, so that's why it's 120 degrees. It makes a trigonal planar. It's in a flat plane. This one here is the basic shape, tetrahedral, AX4. This one here is a tetrahedral that has a lone pair. So this is called a pyramidal shape. Looks like a pyramid. Some people call it trigonal pyramid because it's a 3-sided pyramid, not a 4-sided pyramid. If you've ever been to a pyramid, I haven't, but if you have, you know the pyramids are supposed to have how many sides? 4. So I call it pyramidal, even though it's trigonal pyramidal to be very specific. So tetrahedral is the basic shape for this. What molecule would have this bent shape? Water. Very good. Water. 2 electron domains here with lone pairs and then 2 bonded pairs. And then this one is a cool one here. This one we haven't made. This one here is when you have 1, 2, 3, 4, 5 atoms around a central atom. Okay? And this makes a shape here called a trigonal bipyramidal shape. It's got a flat triangle here, and it's got a peak there and a peak there at the bottom. Okay? Now, the cool thing is if you take off one of these and make it a lone pair and tilt this on its side, it makes what's called a seesaw. So the seesaw looks like this with the lone pair on the top. But that's going up to steric number 5. We can keep going with a couple other shapes. There is more advanced shapes, and I'll show you some of those in just a minute. So steric number 2 is linear geometry. The geometries are determined by the number of sigma bonds. So you got 2 sigma bonds here, BeCl, and CO2 also has 2 sigma bonds. It's not total number of bonds. So if you look at this, how many electron domains in this picture here? 2. How many electron domains in this picture? 2. An electron domain is a bonded pair, lone pair, double bond, or triple bond. Quadruple? They don't. Those don't exist as of current. It'd be cool if they did. It would make sense if they did, but unfortunately they do not. So that's why they're 180 degrees apart. This has 2 sigma bonds. Sigma bonds determine the shape there. These are the 2 pi bonds, if you want to think of it that way. Steric number 3. This is called trigonoplanar geometry. Trigonoplanar, this is central atom with 3 things around it. This is formaldehyde, COOH. This structure here has how many electron domains? 3 electron domains. One of the electron domains is a what type of bond? Double bond. It has a sigma and a pi. Thanksgiving pie. There we go. That's a sigma, that's a sigma. All right, next one. Ooh, what's this one going to be? What's its shape called? Trigonoplanar again. Very good. Trigonoplanar again. And this one here would have what? Lewis dot structure would have what? What do you notice about it? Yeah, what's going on with this? They're all O's and that's an N in the middle? Anything you know about that structure? It's NO3. Why does this though have a double bond? Why shouldn't that one have it? Or that one? Yeah, they all have it. Very good. This would be a resonance structure. This is just one of the resonance structures for it. So again, we drew this in this manner. That's correct in terms of its 3-dimensional geometry. Okay, trigonoplanar geometry. This is one of the exceptions to the octet rule, BF3. Boron only has 6 electrons around it. 2, 4, 6. It has how many electron domains? 3 electron domains. It doesn't have any double bonds though. This one has 3 electron domains and does have a double bond. However, what do you notice is different about this? The angles. Here they're all 120. Here the oxygen actually takes up more space and the electrons around oxygen push the hydrogens a little further away. So it's not quite 120. It's about 121.9 to be exact. And this is 116.2. So again, if you don't have the same things around it, you can have some bending of these angles. So this is a deviation from ideal. The oxygen with more electrons needs more space. Needs to take up more space there. It has a greater electronegativity as well. So the electrons that are shared here are even found closer to the oxygen. So there's lots more electrons in this location, and those electrons repel the electron domains here. Now, for something like this, we've got some basic shapes down. Now let's look at a Lewis dot structure of SO2. In SO2, how many electron domains do you see around the middle S? Try again. How many electron domains? Trois. Dos. Trois. No. There are 3 electron domains. 1 electron domain, 1 electron domain, 1 electron domain. Lone pairs count? Yep. Electron domains, let me see if I can. This is an electron domain because it's a bond. This is an electron domain because it's a lone pair. And this is an electron domain because it's a double bond. Okay? So if we look at this shape here, oh, I knew this was going to happen. Let me fix this. I knew that was going to happen. So because it's got 3 electron domains, the lone pairs push away the bonds. 3 electron domains. What's going to be the shape of this molecule? Okay, its basic arrangement is trigonal planar. Okay, then if we just look at the shape of the molecule, it would be bent. Trigonal planar, it is bent or V-shaped, and that is your SO2. Okay, questions, clarifications on SO2? Yeah?
So why isn't there a double bond on the O and then you get rid of the 2 on the O?
Why isn't there another double bond here? Alright, if you had another double bond here, then it would be 2, 4, 6, 8, 10 electrons around O.
What if you got rid of one of the O? Like the bonded there?
So if you took one of these and put it here,
Yeah.
so you put a double bond there, this would have 2, 4, 6, 8. This would add 2, 4, 6, 8, 10 around the S.
Well, what if you got rid of the 2 on top of the S? Like,
Where would you put these two? You gotta put them somewhere. You can't just make them disappear. And if you did, that would be a positive ion, which might be more stable. But SO2 without a charge, this is what it would look like. Yeah, good question. Yeah, it'd be nice if you could just get rid of an erased electron. Sometimes people do that on a test. They'll draw a Lewis-Dot structure and they'll draw them really faint, like this. They'll be like, see my electron there? Make sure you make them dark because you get no points if you're asked to do this on an AP test. Now, or a test that I grade, so we don't want that to happen. All right, BH3. BH3 is trigonal planar with a bond angle of 120. SO2 molecule is bent with a bond angle of approximately 120. The angles are both the same, but in this case, you have a lone pair here. So the angles look almost exactly the same, you're just missing that extra atom. So this is why these two shapes are quite similar, again, except as that trigonal planar basic shape. Steric number 4 is tetrahedral geometry. Methane, the electron pairs repel, and it is not found in a cross shape. Now, a lot of times it's difficult. How do you draw a tetrahedral shape? This one here is a great way of drawing it with 3 dimensions. Okay? The last one is a dotted angle, and sometimes it's drawn like a little more like a triangle with an up and a down and a coming out towards you is how it's trying to represent. This is what it looks like with a ball and stick model, 109.5 degrees between the CH4. Now, if you're really bad at drawing, here's a way of doing it. Again, to draw methane, sometimes I do this to make it really easy. Okay, it's not the perfect drawing, but it does represent that there's 3 dimensions to it, even though it doesn't look quite as good as the other ones. Yes?
Do you need to know how to draw them in 3D?
You will want to, because if you draw them like this, and it's asking for a 3D picture, that would be wrong. This one could be right, or this one could be right. So I would learn how to draw it like this or like that. I would accept that as well. That's I can't draw, and I'm going to do it that way. I learned how to draw it this way up here on the top. Okay, you do a C, an H, an H. Bring this one out a little bit, an H, and then bring that one back, an H. But I'm not a great drawer, so I never got good at that. Yeah. Trying to represent that it's going backwards. Yeah. I'm not, the people that tried to draw these, again, some were artists and some were not. So most people that can't draw come up with a shortcut to make it look 3D. Now, tetrahedral geometry was shown by our balloons. A tetrahedron is a three-dimensional shape that looks like this. Okay, there's a tetrahedron. A regular tetrahedron looks like this, and at the center of the regular tetrahedron is where the central atom is. A tetrahedral molecule, you eliminate all the sides of the tetrahedron for the picture purposes. And the angle between each of the bonds is 109.5 degrees. NH3 here is a tetrahedral electron geometry molecule. The lone pair causes a repulsion, and the general shape when you remove, when you don't have an H here, is a trigonal pyramidal shape. The ideal tetrahedral should be 109.5 degrees. But because of this lone pair, what does it change the angle to? Okay, 107. Does that make sense why it would do that? Lone pairs repel more. Lone pairs require more room than bonded electrons. So what ends up happening is the shape looks similar to this. Bonded electrons will form a shape that has, again, less repulsion. Here, the non-bonded pair actually extends out like a big fat paddle and sticks out, and so it ends up repelling the electrons of other bonds or of other lone pairs. So it says non-bonded pair, that's also called a lone pair, just so you don't get confused with the language. Here, if you have water, there are how many lone pairs on water? Two lone pairs, so its shape becomes bent, molecular geometry. Okay, the shape, though, is not 109.5 degrees, the angle. The angle is actually going to be what than 109.5?
104.5.
Okay, less, 104.5, because it has two lone pairs. Two lone pairs are repelling more. So that's another way of remembering that. So 109.5, 107, and 104.5 are some angles to remember. So here is the effect of the lone pairs. 109.5, 107, and 104.5. 104.5, 107, 109.5. 109.5, 107, 104.5. Why should you memorize those? Just in case they ask you what the angle is, and they may do that. If you don't know the exact number, all you have to do is make sure you say it's less than 109.5 here, and you'll be in better shape. Just as a hint. Now, when you get into Steric number 5, this is a trigonal bipyramidal shape. PCl5 makes this particular shape. You'll notice there's 90 degrees between the equatorial chlorines and the axial chlorines, and 120 between the equatorial chlorines. This is a trigonal bipyramidal geometry, and there are some molecules that have this particular shape, especially ones with the D's. Third row can have this shape. The geometry here looks more like this with the balloons. Okay, you've got 3 around and 2 on top and bottom. And there's the three-dimensional trigonal bipyramidal shape. Here's what it looks like and how the molecule looks based on that view. From the top, it does not look much different than trigonal pyramid, but you can see you have 2 that are 180 degrees apart from one another. Now, this is one thing that people were asking about the lone pairs. Here, SF4. In this case, with SF4, the F's do not form the equatorial plane. They do not flatten out in this with the thing sticking out of the bottom. Because of this repulsion, the axial lone pair will not occur. The lone pair is only going to be found on the equatorial lone pair because it will have less repulsion. Here it has 3 90-degree angles. Here it has only 2 90-degree angles. Does that make sense? So the F is 90 from this. The F is 90 from this. Here it's 120, 120. Here, all the F's here are 90 except this one. So that's why an equatorial lone pair can happen, but a axial lone pair will not. This molecular geometry is called a seesaw because if you tilt it on its side, the F's on the side here are the base, and here's where you're sitting, and here's where the big person's sitting that's throwing you up in the air. You want to see that picture? Seesaw. May not have ever been on a seesaw before. Maybe you have, maybe you haven't. It's also called a lever by physics people.
Yeah, it's a lever. It's still on the first.
It's a lever. Here's Kevin.
It's evidently a lever.
Who's on the other side? Charlie? Hey, Mr. Christopher, that would be dangerous. Kevin might die. I don't weigh as much as little as I used to. All right. So, Mr. Christopher, Charlie, I won't have you kill Kevin. So, Mr. Christopher sits on it. Kevin sits on it at the same time. Mr. Christopher jumps up in the air, lands. Kevin. All right. Then Kevin does a front flip, lands on it, and hurts me. All right. Can you do a front flip? Dang it, I can do a front flip. All right.
Do it. Do it.
I used to be able to. Sorry. Back when I was your size, Kevin. All right.
That's impossible.
Hey, you would be amazed at how small I was. All right. Now fat I am now. Okay, so BR, F3, sorry. No comment on that. Hey, I ate too much during Thanksgiving. So BR, F3 looks like this. This is when you got the two lone pairs attached to the BR. Here's our three Fs. This is called trigonal bipyramid, the basic shape. Right here, when you remove the lone pairs from it, it makes a T shape. Now, it looks kind of like not a T, but if you tilt it on its side, it makes a T, I guess. I don't know why they draw it that way, but that's a T shape. Here, if you have something like this with three lone pairs, here you've got 90 between these, 90 between these, 120 between these. Which of these would be most likely to occur, A, B, or C? So out of these three, looking at these three, the one that is most likely to occur is the linear geometry, C. Because these are 120 degrees apart with the lone pairs because of lone pair repulsion. So this is called a trigonal bipyramidal electron geometry and a linear molecular geometry. All right, steric number 6. We didn't have that on the chart. Is a octahedral. This is where it looks really cool and is really fun to look at. Not a lot of times you deal with these, but it's still cool. Here, SF6. There's 90 degrees between each F and 90 degrees between each F here. So it makes an octahedral shape. Here's it with balloons. Here's it with an octahedron. Okay? If you ever play die games with octahedral dice, again, it looks like that. A jack? Jack? Yeah, it does look like a jack. Do you have any jacks? If you find a jack, bring it in. I haven't seen a jack in a while. I want to see if it looks the same. I can't Google it right now. I'm so busy. All right. So here's the top view and the side view. Now look at this one. This one looks fun. How many electron domains are on the VR? 6 electron domains. So it's got steric number 6. Its electron geometry is still octahedral. But the lone pair is going to be on any of these. It doesn't matter where it is. But this makes a square pyramidal shape. And here's our square with the pyramid on the top. So the lone pair affects the shape, makes it a square pyramidal shape on BRF5. This one here is another option with xenon and fluorine, XeF4. The two lone pairs are as far apart as possible from one another. And this creates a square planar. The whole square is in the same plane. Here's FF6, octahedral. This is square pyramidal, SbCl5 2-. And XeF4 is square planar. So here's some examples of some molecules that have those particular shapes. So once you get into the octahedral basic shape, you go octahedral, square pyramidal, and then square planar. So these are most of our shapes we've looked at so far. Linear with 2 electron domains. Trigonal planar with 3. Bent, again, should have 4 electron domains if it shows the lone pairs, which it doesn't. Here, tetrahedral basic shape. Trigonal pyramidal. This is a pyramid like ammonia. Trigonal bipyramidal. Seesaw, octahedral, and square planar. So if there are 2 electron pairs, okay, 2 electron pairs, the bond angles is 180 degrees, the underlying shape is linear. If there are 3 electron pairs, or 3 electron domains, the bond angles are 120, it's trigonal planar. If there's 4, it's tetrahedral, 109.5. If there's 5, it's 90 and 120, trigonal bipyramidal. If there's 6, it's 90 and octagonal. So, if you haven't written down some of these angles, please take a moment to do that. We're going to take a quick quiz in about 1 minute. It's not referring to phase here. So electron pairs, I believe that's referring to bonded pairs. You're smart. Octagonal is I can at least study it. Yeah, if you'd like to take pictures, you're more than welcome to. I'll stand by it if you want. No, that was reference. Yeah, that's what I'm ready for. Don't ask me, man. I don't know why people do the things they do. If I understood that, that'd be really cool. Well, all right, ladies and gentlemen, at this time I've got a quiz for you. You got 2 minutes? 2 minutes to answer the following question here. On your mark, get set, go. dot structure first. Lewis dot structure first. You have it? All right. At this time, everybody look forward towards the board. Everybody look at the board. Look at the board right there. Okay. All right. Raise your hand if A is the answer. Down. B the answer. Down. C the answer. All right, so it looks like a lot of people are saying it's either A or B. So I'm going to give you a couple more minutes to work with either the people at your table or at another table to just try to determine what you think the correct answer would be. All right, let's revote. Revote. All right, looking up here. Looking up here, I'm not going to count, but I'm going to count by survey. Please raise your hand if you think the correct answer is C. Yeah. 2. Correct answer is D. Correct answer is A. Correct answer is B.
You feel awfully unsure about it.
All right, unsure. We feel unsure.
Oh, I'm sure.
All right, that's okay. You can feel unsure and still make a guess, right? So you can guess one of them and feel unsure. You can't guess both and feel unsure.
Can I guess both?
No. Now, let's go through this problem because there is some unsurety. So to get sure of what you're doing, the first thing is OF2. If you're sure what you did, please be quiet for other people's unsurety. If you're not sure what you did and you're still talking, please talk to yourself outside or in the bathroom. I'm fine with you talking to yourself all you want. All right, OF2. So we got an O in the middle because O is less electronegative than the F. We got an F, we got another F. So based on our Lewis dot structure, that's the first thing I do with any of these. O has 6, F has 7, and there's 2 of them. So 14 plus 6 is a total of 20 electrons. So we put a single bond between them. 2, 4, 6, 8, 10, 12, 14, 16. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Sorry, bad counting. We've got 20 there, including the double bond, the 2 single bonds. Now, this here has 4 electron domains. You guys should be able to tell me what shape it would be. A tetrahedral basic electron shape. And if you, again, take away the lone pairs, it's what? It's bent shape. It's got the 2 lone pairs, it's bent. Okay, the angle to something that is bent is less than 109.5 degrees. Okay, if it was water, it'd be 104.5 exactly. So it's probably around 105-ish. The O3. Well, most people chose that. So let's look at the C. Why isn't it C? Here you got C, N, N, H, 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 H. For this, N has 5, H, there's 4 of them. And then you have a positive charge, which means you lose 1 electron. So 9 minus 1 is 8 electrons total. I got 2, I got 4, I got 6, I got 8. This is the ammonium ion with a positive charge. And ammonium ion has this particular shape with a really poorly drawn tetrahedral shape. You subtract 1 because it has a positive charge. Positive charge. Okay, because electrons are negative. Yes, Mediha. It's going to be less than 109.5. Water we know is about 104.5 degrees. The reason this one is a little bit less has to do with fluorine. Fluorine is more electronegative than hydrogen. And so oxygen with its lone pairs here, these are repelling, but not quite as much because of fluorine's extra lone pairs. So you can think of it that way. Fluorine's got lone pairs on it as well. Gets really messy, but that's one of the reasons why it's not quite 104.5. I don't know this angle memorized, so I'd have to look that up. I know waters. Yeah. 109.5 less. Yes, you got it. So the O3 is the last one. O3 is the last one. We got O, we got O, we got O. Single bond them up. There's 3 O's, so 6 times 3 is 18. Here we got 2, 4, so I got 14 left. So 2, 4, 6, 8, 10, 12 maybe, 14. It's about as good as it gets with O3. O3 again has resonance structures, but each one of these now has 8 electrons around it. 2, 4, 6, 8, 10, 12, 14, 16, 18. I did do the right number of electrons. But this shape has how many electron domains? 1, 2, 3. 3 electron domains. That means that the angle between these O, double O, O, and the lone pair up here, the angle between these two is going to be about 120 degrees. Maybe a little bit less than 120, but not much. It's going to be about 120 because this shape here, the angle between all of these is 120. It's a trigonal pyramidal. No, I'm sorry, not trigonal. Trigonal planar, sorry. Planar, I meant to say planar. The reason it's trigonal planar is there's 3 electron domains. Or it's got a steric number. It's got 3 electron domains with the lone pairs. So trigonal planar is its basic shape. You remove the lone pairs and you get the bent shape of ozone. The angle is still about 120 degrees. Okay? It is called bent or angular for O3. 120 is greater than 105 and 109.5. So the one with the largest bond angle is ozone, O3. All right, ladies and gentlemen. We've got a break for the next 10 minutes. You may, again, work on anything you would like to during this time.
What are we doing next?
You will probably go home, or you might like stay around the school and hang out with your friends. You might go to that pizza place and give me a donut. No, they used to have them. They weren't donut, garlic holes. That's what they're called.